the last talk of this session is by Victor Miraldo, who will present an efficient and generic algorithm for computing the diff between values of any algebraic data type.
Indeed. Thank you, Zoe. My name is Victor. I am a PhD student at Utrecht University, and Wouter Sviestro is my supervisor. And today I'd like to talk to you a little bit about our latest endeavor in structural differencing, particularly our latest algorithm. But I think it's also fairly important to actually give our angle to this problem. Why do we particularly care about this problem? Well, we are trying to have better programming languages in general, which includes better tooling. And we actually want to solve less painful but superfluous merge conflicts. So we have a typical motivation where you have your little supermarket, and somebody keeps track of that in some sort of Word document, which is a great idea. And somebody changes a little piece of information in this document. Somebody else changes another little piece of information about this document. And eventually, somebody wants to reconcile those changes. But if our differencing tools can only look at the line level, they will never understand that although in different parts of the file, these changes cannot be automatically reconciled, because the same line changed in two different ways. Which suggests that we should actually have some sort of control over what is the structure of, or what's the granularity of the changes we want to look at. So if we're talking about a programming language, we want to look at the changes perhaps at the level of statements, maybe at the level of variables. It doesn't really matter. So to be able to merge these automatically, we need to know about the structure, and we need to encode the differences in such a way, which basically brings us to our first contribution, which is how do we actually represent changes. So we first start by representing the changes in a way that we have access to this structure. Then we also need an efficient algorithm to compute that, because if we plan to be computing hundreds of diffs per day, this needs to work significantly fast. In our paper, you'll also find a generic Haskell implementation. So this will work for any abstract syntax that you give to it. It works over mutually recursive types, even though my slides, it's just a very simple 233 for illustration. And we also evaluated against a real data set from GitHub of over 1,200 actual commits. So we have some actual empirical evidence, which I'm going to get to later on. Instead of talking about the technicalities, however, I think it's more interesting to talk to you a little bit about what motivated us to try this approach, and a little bit about what failed in the previous approach. So we start with the most known tool, I think, for pretty much everybody in this audience, which is our quintessential UNIX Diff. It is the witness of the line-by-line differencing algorithm, which we all use every day, pretty much. And we can have a quick example here, where if we have two different versions of a given file, and we run the UNIX Diff over these versions, it's going to give us a patch that looks something like that. That includes some information about where the change happened. It also includes what was the particular change that happened there. Internally, however, the UNIX Diff uses a little bit of a different representation to be able to compute this object. It uses a very local, a very intentional representation for changes, in which it allows us to insert lines, delete lines, or copy lines, and this is what we call the edit operations. And it bundles them together in what we call an edit script. And essentially, that little example, it's actually seen as copy the first line from the old file to the new file, copy the second line, delete the third line from the source file, and then insert a new third line in its place. And we just write it that way. The way to compute this can be pretty complicated, but nevertheless abides by a simple specification. So the UNIX Diff essentially enumerates all possible edit scripts between the source and the destination, sorts by the most copies because we want to share as much as possible, and just gives you one of them. So abstractly speaking, diffing in general can be seen as a little tool that gives you the differences between two objects of a type A, encoded in what we call a patch of type A, which is essentially a transformation that can be applied such that certain things actually hold. In particular, we are concerned with correctness, but you can be concerned about different things. And the UNIX Diff works for list of strings. So the question for my PhD is basically how do we give this abstract formalization of the diff interface to more types than just list of strings? Well, What has been done so far and is to just reuse what we currently have for the UNIX Diff and say, well, a tree can also be seen as a list. So why not insert tree constructors and delete tree constructors instead of inserting lines and deleting lines? And then, if we are to diff these two trees there, which essentially happens by deleting the bin and the u, we can do a pre-ordered traversal, we flatten those trees, and then we just reuse the UNIX diff, right? Well, then how should we diff these two trees then? What is the subtree you are expected to copy here? You don't know. You might copy u, and this yields an added script with 2 copies. You might copy t, and this yields an added script with 2 copies. And we have no idea which one is the better one. We don't know what's the best option. And somewhere along the implementation of this, on the design or somewhere, somebody's going to be making an arbitrary choice, either an heuristic or some domain expert, but eventually the result of your diffing algorithm will be a little bit unpredictable, which is mainly because the edit script with the most copies is not unique. There are more than one edit script with the most copies, and which is pretty much the source of this problem. In the linear world, however, it's not that much of a problem because the UNIX diff uses the longest common subsequence, which basically considers lists of atomic things, and we just accept as a drawback that we cannot swap things, we cannot permute things, and that's okay. But the moment you look at this list of things and they are not atomic anymore, you lose a lot of expressivity, especially because if we are to apply this to software, well, refactoring style changes happen all the time, and if we cannot really represent those, then we are a little bit in a problem. But besides that, besides not being able to not explore all the copy opportunities as the specification would actually suggest, this actually makes the algorithms pretty slow because it introduces choice points that we cannot ignore. We do have to go over all the choice options, and only after we unfolded the whole search space, we can say, oh, I'm actually going to be choosing this patch. Which tells us, and this is an interesting lesson that I learned from while doing this, is that generalizing this problem actually requires a generalized specification as well. Borrowing the specification from the linear world to the tree-structured world is perhaps misguided. And we actually suggest instead that we just use a very extensional approach. And we say, well, just drop edit scripts altogether, and let's have a completely deterministic diff algorithm with a single best option, and let's just write the change exactly as we expect. Let's write a little lambda abstraction there with a pattern on the left-hand side that matches some meta variables, and then we inject the change on the other way. And this does exactly the swap you expect, and it copies all the possible opportunities, which is basically our new change structure. And for example, here we can see that we have 2 t's on the source there of the diff, and we don't need to choose. We can just say, hey, I have 2 meta variables there that are the same, so they should eventually be the same as well when you apply this, otherwise it's going to fail. And this enables us to copy all of the potential subtrees that can be copied. But moreover, it allows us to write a diff function that is linear in the size of the source and the size of the destination. And that's basically the main advantage of going from a very intentional representation to a little bit more extensional view of what this patch actually does. The way to encode this is not that complicated. In fact, we just seen pretty much everything. We say that the change is essentially a data type annotated with holes. And if we have a simple data type like this 233 there, we simply make another data type called a context. We add another constructor to it, and we just plug some information there. So this essentially allows us to have data types with holes. In the actual paper, we do this for mutually recursive types, which requires you to add 1 constructor per type, which is a little bit more intricate, but still. Applying these things is also exactly what you would expect. It amounts to pattern matching. So here, the application function for this patch illustrated there will essentially require a given structures, which is a bin node. Within a bin node, will also require some opaque data to be there, in this case, the T tree. And when that's the case, we just return the expression side of the patch, injected with the instantiation we discovered when pattern matching. Which brings us to, why is this any good? Why should we be doing this in the first place? Well, it's because we have a better algorithm, and pretty much because our representation enables us to copy as much as possible, so we can drop all the choice points. which means that we can divide our algorithm in two parts. We have a computationally hard part that we're going to apply some black magic to, which is to identify what are the subtrees in S that are also in D and vice versa. And we have an easy part, which is to just extract whatever is not in this set. So we can specify the hard part with a very simple yet very inefficient function, which simply enumerates all the possible subtrees of the source and the destination, computes the intersection, and then returns us a function that, given a tree, tells us whether it's present there or not, and if it is, also tells us which one it is. It needs to be injective on that little fragment, naturally, because if we are to consider duplications and contractions, we need to make sure that we're not breaking anything. That's pretty slow, naturally. We don't like that. So what we do is akin to hash counting or macro trees, or we basically annotate everything with hashes. We put these hashes in a search-efficient data structure, and we can provide an amortized constant time lookup, which is pretty nice. In fact, after we have that, extracting the context becomes almost trivial. It's very natural. You just traverse the source tree and the destination tree, asking this database lookup at every point. If it's supposed to be copied, we abstracted it by a meta variable. If it's not supposed to be copied, we peel one constructor away, and we recurse over the children. And the actual diff function can be written in arguably one line of Haskell. And it's also pretty easy to see that, well, since our Oracle, our WCS function, which stands for which common subtree, is efficient, then so is the diff, because the extract function is also clearly linear. But we would like to have a little bit more information on that. So we went to GitHub, and we mined lots of merge commits, particularly those that git merge actually failed. So we went around the top Lua repositories, and we got all of the merge commits that actually had human intervention. And this gave us about 1,200 commits in which we diffed, and this is 75% of our data set, and this is the whole data set. There's a little zoom on the graph there. And here we have a plot of, on the x-axis, we have the size of the source plus the size of the destination, and then time on the y, naturally. And here, what we've done is we have parsed the files, we have translated them to the generic representation, computed the diffs, and then applied the diffs and checked that the result matched the destination. So it's actually pretty encouraging to see that for a significant number of files, all of this actually happens in very fast. So it can actually be deployed and can be used on a daily basis on an editor or something like this. And especially because we are actually paying the price of generics, which is usually not low. We're also paying the price of cryptographic hashes, which is also not low. So if we actually want to speed this up, we still can. There's still room for it. And well, naturally, I couldn't really finish without talking about merging a little bit, which is, in fact, our main motivation, unfortunately, not for this paper in particular. But we did define a very simple merging algorithm, which does go back to my introduction, that we just check whether the changes happen at separate parts of the file. And if that's the case, we call them disjoint, then they trivially commute. Then we don't have to do anything. And essentially, the merge square would look something like this. We just apply one change that would change some statement in a function, another change that changes a statement in a different function, and as long as they don't insert anything, they should commute. And as it turns out, actually, we could already trivially solve 11% of the commits that git merge failed, so without doing anything. So this is just even the implementation is just a single line of Haskell, which shows us there's good potential here. We had the ability to be able to compute these objects in an efficient manner, and without doing any fancy things, we actually are able to already solve 11% of it. So I'm eager to see what we can do doing fancy things, but that's, I guess, future work. Which also brings us to the fact that there's no free lunch, so there's still a number of open questions we are working on, and I'm happy to hear what you guys have to say about this later on. But for example, this new representation being very extensional is also very hard to reason about. So the merging algorithms, essentially, we want to prove that the merge result is actually commutative and things like this, and with an intentional representation, you have an easier time formalizing this. At the same time, by dropping the existing meta theory, we have a little bit more work to do to actually place this correctly within the meta theoretical possibilities that we can. We also can't, for example, copy bits inside of a tree, and then there's the question about, does is this actually a problem? Does this make sense? So there's still a significant amount of work to be able to bring this from a PhD laboratory to the actual real world, I'd say. But all in all, we did achieve a very interesting algorithm with a very clear division of tasks, which is very nice because it makes it very configurable. It is deterministic as well, so we can actually calculate, we can predict what the result of a diff is going to be, which is not the case with the UNIX Diff. If you ever try to do that, you'll see that you're going to be very surprised. We can actually express many more changes than edit scripts because we have the ability to do permutations and etc. And we do achieve an overall faster algorithm than the approaches using edit scripts, whatever the edit operations they choose. So I'd say that overall we have presented here a very fast and a generic algorithm, and we have some encouraging empirical evidence that this can be used in practice. So we are excited to move forward and see how else can we apply this. And I hope that you guys have some good questions for me about and good suggestions about how we can do this. Thank you very much.
I will start with a question from Slido. The title says type-safe diffing. What exactly does that refer to?
So the type-safe really means that a patch of a type A is guaranteed to return a value that is well typed with respect to that. So we never produce, there we go. And which means that we never produce ill-typed things, which in turn really means that everything that we do is going to be able to parse. So even if you manipulate these objects, you're never going to produce something that doesn't parse.
Yes, please.
So one aspect of your work using generics means that lists are going to be treated as just a tree, whereas a more traditional, say, diff-like algorithm would be able to describe just inserting into, say, the fourth element of a list, or swapping to moving an element around in a list. Mm-hmm. Would that be something that you could add to the system that you've had so that you could treat sequential data structures specially, or have you thought about that?
Yeah, definitely. So what you can do is you can make a domain-specific generic library that would just add the list structure as a particular thing, a built-in type in the system, and then you can definitely handle it in a special way.
One more question from Slido. On the surface, it seems as though you could just convert both structures into a single Merkle directed acyclic graph and traverse both routes. Is your method superior in some way?
I do not immediately see how we could do this, but I'm happy to take this question offline and actually see how you could do this with DAGs.
How did you go from the Lua source file to trees?
With the Lua parser from language.lua.
Okay, so it's representing this AST tree structure from the source files, basically.
Yeah, so it works after the AST. So basically the deal is the user gives me a parser and I give him the diffing framework.
Any more questions from the audience?
Hi. So there are some well-known examples of line-based merging on source code that led to bugs, automatic merging. Like there was a authentication error in some iPhone protocol, I remember. So do you think this is safer, and do you have any evidence for that?
I don't have evidence, but I do think it is safer, particularly because on those patches, particularly on the iPhone one I've seen, it was actually because of a duplicate statement. So if you are to merge this, it is actually also going to require that the statement is always going to be duplicate. So it's never going to erase something that's not supposed to, or at least it's going to be easier to spot.
A question from Slido. In Git, UNIX Diff is used on trees as lists, the directories. Have you considered your algorithm there?
So it's used on directories, but at the same time it just lists the directories and then basically diffs that list of directories. We could just use that instead, and I haven't considered, but that's just rows trees, so it should be plug and play. Famous last words, though.
We have time for one more question.
I think you said your algorithm was linear time. If you then apply it to strings again, do you get a linear time longest common subsequence?
Well, no. It's not granted that this is always return the longest common subsequence. That's also one of the problems that detaching from existing meta theory.
Thank you all very much.
Thank you.